Hello students, my name is Shashank Shekhar. So we have started the chapter Haloalkanes and Haloarenes, and we have covered the part that is nomenclature of the compounds and the nature of CX bond. Earlier we have seen the classification. So if I talk about the nomenclature, so we will just keep track of this nomenclature for each of these reactions. By which I mean that I should be using the names of the compound, and you should try to build a relevance that the name I'm speaking then and the name you are imagining should be matching. Okay, so you should keep that nomenclature in your mind. So if I talk about the syllabus, so we have covered this part. Up till this part we have covered it. Sorry, this one. So we'll be starting with the physical and chemical properties. Basically, first of all, we'll see the preparation methodologies that are used for the preparation of haloalkanes, and we will only focus on 2 to 3 methods today. The rest of us we will cover in the next lecture. Okay, now if I talk about the syllabus, the topics covered to be today. So the first of all, we will just give a quick revision to this nature of CX bond again, because this is important in the chemical reactivity part also. Okay, now then we will move to the preparation part, starting from alcohols, then from alkene. Now the preparation from alkene involves certain complexities which you must have studied in your say 11th class, but I will still give you a revision of that, because it is very important during the examination time to keep a track of all this mechanistic part of this Markovnikov's and anti-Markovnikov's rule. They are very important for our examinations. Okay, so talking about our previous class, we have studied the nature of CX bond, where we have seen that in C and X bond, the electrons are more pulled over by the halogens because they are more electronegative. Due to this reason, there is a kind of development of delta negative charge on the halogen, and as a result of it, due to the attraction of electrons, or you can say the movement of electron towards the halogen, the carbon develops a delta positive charge. Then we have further discussed the bond length also. Due to the small size of this fluorine, then we have chlorine, bromine, iodine. So this is the increasing size of the halogen atom, because as we move down the group, the size of the atom increases due to the increased number of shells. So therefore, we have this bond length, because as the size increases, the distance between the carbon and fluorine also increases, and that is considered as the bond length. Therefore, you can see that on moving from 139 to 178, then we move to 193 and 214. So the bond length is increasing. This bond length is given in picometer. And next is the bond enthalpy. So since bond length is smaller, so we will have to put up more energy to break this bond. Therefore, this has the largest bond enthalpy. Then we have this 351, then 293 and 234. So talking about this bond enthalpy, this is for the 1 mole of a bond. So if you take 1 mole of a bond, or you can say that there are 1 mole CF bonds or 1 mole Cl bonds, and the energy that is required in kilojoule to break those bonds, that value is mentioned here. So you should just look at the say this terminology more accurately, because you are a science student, so you must be well aware about these things. Okay, so do not just see the values and say, okay, this is low or this is high. You have to look at this one also, that it which term it is given. To have a idea of these values would give you a more proper you can say perspective to look at these things. Then I also mentioned that the dipole moment should decrease down the group, because the electronegativity is decreasing. But the fluorine, being in the same period as carbon, is able to donate its lone pair to the carbon, due to which the electron distribution, or you can say the electronic distribution, is distorted, and the dipole moment of this say carbon fluorine bond is less than our carbon chlorine bond, because chlorine is larger in size and its electrons are present at a higher energy, so it would be difficult for chlorine to donate it to carbon. Therefore, we can see that its dipole moment is as usual higher than the fluorine. Then we have this order. So if I talk about this dipole moment, then it would look like this. So the first One, the CCl will have the largest dipole moment. Then we will have CF. Then we will have bromine, and afterwards we will have iodine. So this is the dipole moment order. You should remember this thing. So you can be asked in the exam, and there is a possibility that you will make the mistake by seeing at the electronegativity. So this was all about the nature of CX bond. We have yesterday covered it, so I have just given a quick revision of it. Now we will start with the preparations. Now if I talk about the preparations, this hydroxyl group can be used, or the alcohols can be used for the preparation of haloalkane. And how it can be done? If we react it with halogen or acid, phosphorus halides, and thionyl chloride. So three ways are possible to use this alcohol to prepare our alkyl halide. So starting with the thionyl chloride. So what do? We react this ROH with SOCl2, then it would result in alkyl halide and SO2 and HCl. Now this process is the most efficient one. Why? Because the byproducts, that are the sulfur dioxide and HCl, they are present as gas. This makes our purification easier because the RCl that is obtained is, say, it can be solid or liquid depending upon the length of this R, but it will not be gas. It will be not be gas certainly. So due to this reason, it can be purified easily. We do not need to do any further purification methodologies to extract our product. Therefore, it is a most efficient method in which we react this ROH with SOCl2. So if you want to look at the mechanism, that would look like this. Say we have ROH and we have SOCl2. Okay. Now this lone pair will attack here. It will move here and revert back, and this Cl will be kicked out. And we will get this kind of adduct. Okay, not adduct, I would say. We will get this kind of intermediate. Now what will happen? Now this Cl will move here. This Cl will attack here. Okay, so the Cl which was kicked out, it will attack here, and we will get back this thing. So did you get my point? So it is a kind of SNI reaction, not SN1 or SN2, SNI. So we get back this RCl, which is our required alkyl halide. Next thing, the reaction of primary and secondary alcohol with HCl require the presence of catalyst ZnCl2. Now this reaction is very important. You will see this reaction as Lucas test when you will study alcohol chapter. So then you will see this Lucas test. So I will not give the mechanism here, just we will talk about this reactivity, because the mechanism will be more approached during that chapter, that is alcohol. So if I talk about the relative reactivities, then it is seen that this tertiary alcohol is more reactive, then comes our secondary alcohol, and then comes our primary alcohol. So this is the order of this. How do we justify this thing? So if you have to react primary and secondary alcohol, then you have to use this ZnCl2. You have to use with ZnCl2. Coming to the tertiary alcohol, the reaction is conducted by simply shaking the alcohol with concentrated HCl. Concentrated HCl. So you have to simply shake it with our alcohol and get our product. So in case of tertiary alcohol, you do not have to add this say catalyst. Now if I want to make alkyl bromide instead of alkyl chloride, then you have to boil it with 48% of HBr. Now if you want to make alkyl iodide, then you have to react it with this potassium iodide in presence of 95% of orthophosphoric acid. So three halogens are present here. Okay, except fluorine, you can prepare chlorine, fluorine, and chlorine, bromine, and iodine. For chlorine, you have to treat with HCl in the presence of ZnCl2 for primary and secondary. For tertiary, you have just to shake with the tertiary alcohol. Coming to this alkyl bromide, you have to treat with this HBr, that is 48%, and you have to do the constant boiling. Next, if you want to prepare alkyl iodide, you have to treat with potassium iodide. Okay, potassium iodide in 95% orthophosphoric acid. Now, if I want to talk about the reactivities of this alcohol with halo acid, so this one, HCl or HBr, then the order is followed, which is followed is this 3 degree, 2 degree, and 1 degree. Okay, this is clear. So, this was the preparation from alcohol. So, we have seen two methods. First was the reaction with thionyl chloride, and second was with halo acid to prepare our required alkyl halide. Now, you can see a exception here that for preparing iodine, you don't have to react it with Hi. Instead, you have to react it with potassium iodide in 95% orthophosphoric acid. So remember these things. Okay, so these are the minute things you should remember. Now next. So the other method that is used for the preparation from alcohol is the phosphorus tribromides or triiodides. You can use either of them, and they are generally prepared by usually generated in C2 by the reaction of red phosphorus with bromine and iodine. So what it is written that if you react the red phosphorus with bromine and iodine, then you will get your potassium tribromide or triiodide. Now this can be px3, x is equals to Cl and Br both. So if you react this thing with this, and how this is prepared? By this method, red phosphorus X2. Okay, so we'll see this thing. So it is a kind of tricky part. Students do make mistake here. So they are given with the reagent reactants. Okay, but now consider that we have our px3 and where x is equals to chlorine or bromine. So what do? We react it with our alcohol. Then we got our this Rx and H3PO3. Next, if we take ROH and react it with PCl5, that is phosphorus pentachloride, then again we will get our alkyl chloride, POCl3 and HCl. So in these two methods in which we use for phosphorus halides, they can be either trihalides or pentahalides. We can use both of them to create our alkyl halide. Now the above methods are not applicable to haloarene because carbon-oxygen bond in phenol has a partial double bond character and is difficult to break being stronger. So what it is written that you can do all these reactions of alcohol with this say different reagent to give our alkyl halide, but you cannot use or you cannot apply the same on phenol. You cannot react this phenol with HCl or say your PX3 to get our haloarene. You cannot do that because the carbon oxygen bond is much more stronger as compared to the simple aliphatic chain. Now if I talk about some other reactions, we have our ROH, NABr, H2SO4. Then you will get RBr, NaHO4 and H2O. So look at this reaction. Does it seem similar to you? Yeah, it is similar. We have only what we have changed. We have placed the reagent reactants, means the reagent which are used for the preparation of the reagent. So I would explain it like this. So if you react your red phosphorus with bromine, so you get this phosphorus trihalide. Okay, so if you react this red phosphorus with bromine, you get your phosphorus trihalide. But and the reaction of it further with alcohol gives you this your halide, alkyl halide. Now what we do not react this first and use it this one. We directly use their reactants in the end we get our products. Okay, so the difference between they are both the same reaction, but what we are doing, we are using the reagents reactant, means the how reagent is prepared, we are using their reactants to directly consume them and convert our alcohol to our alkyl halide. Now the first reaction is the reaction of ROH with NABr, H2SO4 gives us RBr and HSO4 and H2O. So if you want to look at the mechanism, it is nothing but a simple nucleophilic attack. Okay, so you have your ROH, you protonate it with this H2SO4. Now it has become a good leaving group. Now NABr has Br minus. It will simply attack here and you will get your RBr. Okay, this is clear. So this is a short mechanism, description of the mechanism. If you are interested in it, you can take a look at it. Now next is the preparation from alkane. Okay, so this preparation of alkane is basically following this radical mechanism. Okay, so this is following your radical mechanism. Now, why I am saying that it is following radical mechanism, why it is important to mention this? So it is important because it is very helpful in predicting our product. Say we have this reaction here. Now one more thing, free radical chlorination and bromination is only possible. You cannot use iodine because they quickly dimerize. So you have to put a reagent there. I think it is different. I will tell you later on. But you cannot use this iodine here. You can use only this chlorine and bromine. For iodine, you have to use a certain inhibitor which would stop the dimerization of I. I would tell that later. Okay. But for now, assume that you can take chlorine and bromine, and in the presence of UV light, this alkane will be converted into haloalkane. Now, where will the chlorine added? It will depend on the relative stability of the radical. Okay. So the two possibilities are, there are more than two possibilities. Of course, there are many possibilities, and I would say that this halogenation in the presence of UV light, they give us a mixture of monopolyhaloalkane, which is very difficult to separate as pure compound, because this halogenation can not lead only to monohalogenation, it can lead to dihalogenation, trihalogenation, tetrahalogenation, and that would be very difficult to separate also, because the electronegativity difference is not that much that it would become polar, or any other methodologies will not be applicable easily. So it is a very bad method to prepare our chlorinated compound, or you can say halogenated compound, but still we will study this. Okay. And due to this reason, the yield of any single compound is very low. So not you cannot say that this compound is obtained in higher amount. Okay, that yield is not good. It is poor yield. It gives poor yield for a single compound. Now, if I talk about this one, so it can give two here. How many halogenation product can be formed? This is a very good question to ask. Okay, so how many halogenation product can be formed? So first, and monohalogenation, I am talking about monohalogenation. So first we can add chlorine here and here. Now some of you will say then we can add here and here also. But if you see those two compounds, then that would be similar to this two compound. Okay. So if you say that if we write CH2Cl here, then CH2, then CH2, then CH2, and then sorry, CH3, CH3, CHCl, CH2, and CH3. So these two compounds in which we have added chlorine in the first and second position, they are similar to this. So I would say this is similar to this one, and this one is similar to this one. Okay. So do not get confused. Questions are asked that how many monohalogenated compounds are possible. Count the number of compounds that are possible. Do it nicely. Compare all of this. Then only write your answer. Okay. So this forms a very good question. Of course, you will not be asked to use this method as a method of preparation for alkyl halide, because I have told you earlier that it gives you a mixture of compound and it is very difficult to separate them as pure compound. And also the yield of a single product is poor. You cannot get proper yield also. For the time being, if we assume that okay, we are able to say separate them, but the yield will also be low. So this will not be asked as a method to say obtain, or you can say prepare alkyl halide. This would be asked as counting the number of isomers that are possible, or you can say the number of, what are the number of product that would be formed if we are assuming dihalogenation. So this types of question can be asked. Okay, is this clear to you? Okay, now next is the preparation from alkene. So if I talk about the alkene, two products are possible. Okay, two products are possible for a single alkene. For a symmetrical alkene, you don't have to worry. How? Suppose we have ethene. We are given ethene. And you are said that okay, we are adding HBr. Then we can get two products, you would say. This is the H and this is the Br. Now the next possibility you would think of is this one. Here we got our H. So here we got our Br, here we got our H. But if you see, both of these are same. Okay, both of these are same. So I want to make statement here. If the alkene that is present, or is the compound that is present here, suppose that alkene is symmetrical alkene, means substituent on the both side are same. If the substituent on both side of alkene are same, you don't have to worry about the major product, you will get the same product. Okay, you don't have to worry about it. Now what will be the case if the substituent on either side are different? Here the case you can see here, that on one side we have H and CH3 on carbon, and the other side we have both H as the substituent on carbon. So the substituent on both carbons are not same. So therefore you have to think of two products. You can think of two products. If the Br adds on second carbon atom, then this will give us 2 bromopropane, and if it adds on first carbon atom, then it would give us 1 bromopropane. So two products are possible. Now a rule you must have studied in 11, but we will study it here also. It's very important. So that rules are Markovnikov's and anti-Markovnikov's rule. Okay, so it is very helpful in deciding that on which side our Br will go and our H will go. So here is our two possible product for the reaction of ethene with HBr 1 and 2. So this is first and this is second. 2 bromopropane is first and 1 bromopropane is second. Now first we will move to Markovnikov's rule. So what does this Markovnikov's rule said? This rule says that the negative part of the addendum. What is the addendum? The adding molecule is called as addendum. So in this case, this is the addendum where we have addendum. This gets attached to that carbon which possesses lesser number of hydrogen atom. It is saying that the negative part, so which is the negative part here? So out of these two, this is the negative part because it has a delta negative charge due to electronegativity of the bromine. Now the negative part of the addendum, where it gets attached, it attached to that carbon which has possessed the lesser number of hydrogen atom. Okay, so here you can see that we have H2, 2 hydrogen atom here and 1 hydrogen atom here. So which has the lesser number of hydrogen? This one. So bromine will be added here. So let us see why does it happen so. So according to this rule, we have seen that the first product 2-bromopentane is expected. So you must have seen the previous question that this would give the most major product if we are taking the Markovnikov's rule. So this was the first product. Now in actual practice, this is principal product of the reaction, and this generalization was given by Markovnikov's rule. So it can be better understood if we take a look at the mechanism of the reaction. Now we know that this halogen, you can say hydrogen halogen or halohalogens are kind of acid. Okay. Now what happens here is that this H plus of this HBr protonates this alkene. Okay, this H plus of this HBr protonates this alkene. Now this H plus can go here at first carbon and at second carbon. Two possibilities are there. What are the two possibilities? It can go at the first carbon or it can go at the second carbon. Now we are left with two products, two intermediates, I would say. In the first one, the positive charge, since the hydrogen has gone here, so the positive charge is developed on this carbon, and in this case the H plus has been gone here, so H plus is going here, so we get H plus as this positive charge as this carbon. So how it is generating positive charge? Consider the addition of H plus. So this is our H plus. Now what will happen? This pi bond, okay, this pi bond will attack on this H plus, and it will both of this electron will now be shared between this carbon and this hydrogen. So I'm taking this one of this case, it would look like this. Now since a pair of electron has been gone there, we are left with a positive charge on this carbon because this this electron has been removed from this carbon. Similarly, if this uh, electron, this pi electrons are shared between the middle carbon and the hydrogen, then we are left with a positive charge on this carbon. Now two of the intermediates are possible. Now we have to decide that which one is stable out of these two. So if you have studied the inductive effect, then you will be easily able to predict. So why is it happening? So the first one goes like this. Suppose we are adding the H plus here. So we are adding the H plus on first carbon. So it will look like this. And the second one is this one. So we'll have a positive charge here. Okay. Now you will see that which one is stable. How you will decide it? On the basis of alpha hydrogen. So if you talk about alpha hydrogen, so alpha hydrogens are that hydrogens which are present on alpha carbon. So we have two alpha carbons on this for this and one alpha carbon for this carbocation. So how many alpha hydrogen possible? So if we count them, so we have 1, 2, 3, 4, 5 and 6. 6 alpha hydrogens are possible. Whereas in this case we have 1 and 2. 2 alpha hydrogen are possible. Since the number of alpha hydrogen is more, therefore this one will be more stable. This one will be more stable. Why it will be more stable? Because now how does this stabilize it? So you must have studied the hyperconjugation effect. Hyperconjugation effect. So we are using the same concept. I'm not going into the technicality. I'm just giving overview that hyperconjugation effect says that more is the number of alpha hydrogen, more is the stability of this positive charge. Now due to this one is being the most stable one out of those two. Okay. Now since this is the most stable one, this will be formed. Of course, so the stable intermediate will be formed. And now the Br minus, so we have H and Br. So H is gone here on this carbon. Now Br will attack the positive charge. This Br minus will attack the positive charge and we will get our product as 2-bromopropane. How is it 2-bromopropane? First of all, you should try to enhance or grasp this also. So first of all, the longest chain is this one. Numbering is this in this way. Either you do in this way or this way. You will get your substituent on the same number, that is 2. So we have 2-bromo. For 3 carbons we have propane, and this is the major product, that is 2-bromopropane. So this is the mechanism for our Markovnikov rule. Now the second one we have is the anti-Markovnikov rule. Anti-Markovnikov rule. So we call also it as peroxide effect and Kharash effect. Now in chemistry, or you can say in organic synthesis, we want each of the product. Okay, so we find ways, or you can say we find methods so that we can get our required product. So if we add your HBr to this alkene, then you would say that okay, due to the mechanism that is being followed or the product that is being analyzed by Markovnikov, we will get the bromine attached to that carbon which has the lesser number of hydrogen. So this is clear. Now what happens if we want the bromine to be attached on the next side, or you can say to the carbon which is on the next terminal of the double bond? So what we will do for it, we will add our peroxide. Okay, we will add our peroxide. Now the previous method you have seen, that was following a carbon cation intermediate, or you can say carbocation or ion intermediate. Ionic intermediates are being formed. But in this case, in case of anti-Markovnikov rule, we have the formation of radical rather than ions. So the reagent we add here is this benzoyl peroxide. Now what is unique about this benzoyl peroxide? It has a OO single bond. O single bond. And this O single bond is seen that this O single bond is weaker. Okay, as compared to any bond, this is weaker and this easily gets homolyzed, or you can say easily undergoes homolytic cleavage. So what happens that if we do it in the presence of your peroxide, then what will happen? First of all, due to homolysis or due to presence of UV, this bond will break into two. The homolytic cleavage will take place and one electron will be going to each of this. Now, what is the number of electron on oxygen? So 1, 2, 3, 4, 5, 6. Since we have taken this homolytic cleavage, so each of this will get their electron back, and we will have the same number of electrons that are the atomic number of oxygen. What else we will get? We will get this thing decomposed. Okay, so this thing will get decomposed easily because it is not stable. So we'll get this benzene radical. Okay, here. So one H will go and we will get this benzene radical plus CO2. So it will form like this. Suppose we have our C6H5CO O, and 1, 2, 3, 4, 5. So this is the structure that we have. So one of these electrons will go here and one of this will go here. Similarly, one of this will go here. So this hook arrow is showing that only one electron is being replaced. Therefore, we will have a C6H5 dot plus. Now you can see that one electron is coming from oxygen and the other electron is coming from carbon bond. So that would result in a bond. Therefore, we'll get it as CO2. So one phenyl radical and one carbon dioxide molecule. Since we have two of those, so we will get two of those. That is 2 C6H5 dot and 2 CO2. Now next what will happen? So we have our HBr. Again we will do a homolysis, and this dot will take H here, and the Br and H bond electron will be distributed equally among both of this. So Br will take one of this electron and H will take one of this electron, and this electron of H and C6H5 will make a bond and we will get it as C6H3. So is this clear? Okay, so we got our Br radical again. And we got our, here we will get this, not this one, we'll get C6H5. It is not written clearly. Okay, so we are getting C6H5. Okay, now what will happen? Now if you talk about overall reaction, now the reaction says that two radicals are possible. So here we are again getting a Br radical. Notice this one. So we are left with this Br radical. So here will be C6H5, not 3. We are left with a Br radical. And now this Br radical will react with this double bond. Now two possibilities are there. What are the two possibilities? So if you look at it again, so we have our Br radical. So either we get this kind of thing, and this is going to CH3 radical, CH2 radical, that is CH2 radical, CH, here Br, CH3, this one, or either this one. Okay, we have two possibilities, either this one or this one. So two of the radicals are possible. One is a terminal radical, and one is a radical on the middle carbon. Now, what is the difference between these two? Again, let me make a point here that 3-degree radical is more stable than 2-degree and then 1-degree. And the reason is same as our carbocation. That is our hyperconjugation effect. So here also we can apply the same rule, that more is the number of alpha hydrogen, more is the stability of that carbon. Now this will be formed in major amount. This one. Okay, this will be formed in major amount. So here it is written same, more stable secondary free radical. Now this C dot will again take your H from here, and we will get a Br dot back. Okay, we will get a Br dot back, and your product here is that is formed is this one. Now you can see that Br is on the opposite side. So if I summarize both of the reactions, then we have two cases. Suppose our reaction was this. We have CH, we have CH3, CH2. First is if we use benzoyl peroxide, which looks like this. So remember the structure. Okay, try to remember the structure. So its structure look like this. So in this case, the negative part of the addendum, what is the addendum that we are using, or the adding molecule, is HBr. The negative part of the addendum will go to that molecule, or that atom which has the more number of hydrogens. That is our anti-Markovnikovs. I'm just writing anti-Markovnikovs. Therefore, our Br will be added here and H will be added here. On the other side, if we simply add HBr, here also we need HBr. Of course, we need HBr. So here we have ionic intermediate. And here we have radical intermediate. Okay, is this clear? Okay. Now in this case, we will have CH3 here, CH here, and Br here, and CH3 here. So these two products are just opposite of each other. These two products are just opposite of each other. Therefore, this is our Markovnikovs and anti-Markovnikovs rule. Now we can prepare again our alkyl halide using both of these methods. So what are the main differences between Markovnikovs and anti-Markovnikovs rule? So in Markovnikovs rule, the negative addendum goes to that part which has the least number of hydrogens, on that carbon which has the least number of hydrogens, plus it goes through this your ionic intermediate. Whereas moving to anti-Markovnikovs, if we talk about our anti-Markovnikovs, then the negative part of this, say our adding molecule or addendum, goes to that carbon which has the more number of hydrogen atoms, and that is happening that is happening due to the formation of radical intermediate. So these are the two cases, anti-Markovnikovs and Markovnikovs. So we have overall done the preparation of this haloalkane and haloarene using three different starting materials. First was alcohol. So we have seen that various methods can be used. With the help of alcohol, we can make our alkyl halide using various reagents. So likewise, we have our thionyl chloride, in which was the most efficient one. Then we have halo acids. Again, we have this phosphorus trihalides and pentahalides. But what is common is, and one more very important thing I want to mention, that this Kharash or anti-Markovnikovs effect is only applicable if we are adding HBr. Okay, remember this thing, very important point here. So if you apply anti-Markovnikovs rule to your HCl, it will not work. It will follow your simple Markovnikovs rule. It will not have any effect. This peroxide will have no effect on HCl, HBr, sorry, HCl or HI. For HF, we don't have the formula, or I would say that the all the methods that we have used till now in this lecture, they are nothing to do with fluorine. We cannot form alkyl fluorides using those methods. But the point that I want to make here the most important one is that you can use this kharash or this peroxide effect only if you are adding HBr. This is only applicable to HBr and no other halogens, not to bromine, not to iodine. Okay, and fluorine is out of our context only, so we do not have to worry about it. So this is the Markovnikov's and anti-Markovnikov's rule. Now we have first started from alcohols. We have used different methods like our PX3 and PBr3. Okay, phosphorus pentahalides and trihalides. Now remember that reaction in which we use red phosphorus and halogens to prepare our phosphorus trihalides. Next, so this was with halogen. Again, we move to our next part, that is alkane. So what do we do in case of alkane? We do the reaction with our chlorine in the presence of light or UV light, and that also follows our say this radical mechanism. But the problem was there that it was not giving pure compound because it was giving a mixture of compound due to monohalogenation, dihalogenation, or you can say polyhalogenation of the alkane. So you will get a mixture of these compounds, and that would be very difficult to separate because their physical properties are not much that different. Okay, is this clear? Okay. Next, at last we saw that we can do it from alkenes also if we simply add halogen acids, and that also happens to in two ways. The first one was Markovnikov's and the second one was anti-Markovnikov's. So talking about tomorrow's lecture, we will continue with our preparation and we will see that till now we have seen no method that is applicable to synthesis of alkyl fluoride. So tomorrow we will see like Finkelstein method, Sandemeyer method. Sandemeyer is for haloarene, I think. It is for haloarene. You can see Finkelstein method, okay, which can be used for the preparation of alkyl fluorides. So this was for today's class. So in the next class we will continue with our preparation. Okay, thank you.